So far in chapter 2, we've talked about several characteristics of an atom. So depending on what element that atom belongs to, it is different size, it has different number of protons, it has different number of electrons, and therefore it has a different amount of energy shells in which these electrons are organized. One other characteristic of an atom that is important for me to mention is electronegativity. Electronegativity is an atom's ability to pull electrons toward its nucleus, toward itself, the middle of itself. Electronegativity is like how much strength does that atom have to pull on electrons. And this generally is talking about electrons that are in the valence shell or just outside of the valence shell. Atoms with high electronegativity have stronger force of pull, and atoms that have a lower electronegativity can't pull quite as hard. Here you see a periodic table that has elements color-coded by how electronegative they are. And in fact, electronegativity can be quantified, so there's a number that can be assigned. We don't need to worry about the number, but as you see, the more you go to the right of the periodic table, the higher electronegativity, especially for the elements toward the top. So the smaller of the elements on the right-hand side of the periodic table. The reason why this is important is because the difference in the electronegativity of atoms that share electrons in a covalent bond will determine the nature of that covalent bond. And this is really important for the function of that molecule in nature. So if the two atoms that are sharing electrons, you know, they have their electron clouds overlapping when they share a pair or several pairs of electrons. If those two atoms are atoms of the same element, like two hydrogens or two oxygens or two nitrogens, or they are different atoms, but they have about the same electronegativity, like hydrogen and carbon, then the electrons that are shared will be shared evenly, because the strength of the pull of the two different nuclei is the same. So think about the tug of war game, and if your teams on both sides are exactly evenly matched, then the little flag in the middle of the rope is never going to be moved. It's going to be exactly in the middle. So electrons are shared exactly evenly and stay right in the middle between two nuclei if the two atoms have the same or nearly the same electronegativity. And we call that kind of covalent bond where electrons are shared exactly evenly and are located in the middle, we call that nonpolar covalent bond. However, if the two atoms that are participating in a covalent bond have very different electronegativity, one's able to pull really strong and the other one isn't pulling, then the electrons end up being much, much closer to the nucleus of the more electronegative atom. And they stay closer to that nucleus. Therefore, those shared electrons are not being shared evenly at all. They spend more time closer to the nucleus of the more electronegative atom. Those covalent bonds where sharing is not equal are called polar covalent bonds. I recommend that you pause the video to let your brain really process that and then come back for this next part. So sometimes the really strong puller, or the atom with a really high electronegativity, pulls so hard towards itself that it completely rips the electron away from the weaker atom. And now it has an extra electron, so it becomes an ion. And this is lacking an electron because the electron was pulled away, and it is now a positive ion or a cation. And now these two oppositely charged ions can just stick together in an ionic bond. So it's really kind of a spectrum from non-polar covalent bonds where there's equal sharing to polar covalent bonds when the electrons are kind of closer to one atom, to ionic bonds when electron completely went to the other atom and now you have two ions that are attracted ionically. If this spectrum explanation did not make sense to you, please don't worry about it because it's a little bit above the basics that I'm going to be testing you on. You don't need to memorize the numbers that represent the strength of the electronegativity, but I do need you to know the relative strength of the four most common elements found in nature. So hydrogen and carbon both have about the same electronegativity. So anytime you have two hydrogens sharing electrons, two carbons, or hydrogen and a carbon, the covalent bond is non-polar because the electrons that are being shared are shared evenly and spend their time in the middle between the two nuclei. However, nitrogen and oxygen are significantly more polar than carbon and hydrogen. So if there is a covalent bond between hydrogen and nitrogen, hydrogen-oxygen, carbon-oxygen, or carbon and nitrogen, all those bonds are polar. Here's an example, a simple example, a tiny common molecule, and that is water. Water is made up of two hydrogen atoms and one oxygen atom. So H2O is two hydrogens, one oxygen. The top figure, figure 1, shows a very basic model diagram of how the hydrogens are connected to the oxygen. So notice the valence electrons for both of the elements, so for hydrogens and for the oxygen, and how they're being shared. In this particular case, both hydrogens receive one of oxygen's shared electrons, and oxygen receives one electron from each hydrogen to share. Therefore, both the hydrogens and the oxygen have full valence shells, and they're very stable in this configuration. However, the picture at the top, figure 1, is really simplified, and the lower figure is a little bit more informative. Instead of showing all of the electrons, figure 2 only shows the two pairs of shared electrons. And what it's trying to demonstrate is that the shared electrons are much closer to the oxygen than they are to the hydrogen. Notice how right there, I can't really see what I'm pointing at, but notice how the letter H, which is supposed to represent the nucleus of the hydrogen, is quite the distance away from those electrons that it was contributing to the sharing. And this creates an interesting phenomenon. So overall, the water molecule is neutral because if we count up all the protons, the number will equal to all the electrons if you combine oxygens and hydrogens, electrons and protons. We have equal amount of positive and negative charges. However, the two shared electrons from hydrogen are spending their time almost entirely in the sphere of oxygen. So oxygen has 8 protons, 8 positive charges inside, but now it has a little bit more than its 8 electrons because the two shared are also spending time next to it, so it's feeling more of the negative charge there. Whereas the hydrogens actually have less of their negative charge around the nucleus. So if we look at the water molecule as a whole, the side of the water molecule that has oxygen is just a tiny bit more negatively charged than the side of the molecule that has the hydrogens attached, which is slightly positively charged. So although the number of positive and negative charges of this water molecule is equal, that charge is not distributed equally throughout the entire molecule. There's like a crowding of the electrons closer to the oxygen end. And in this diagram, lowercase Greek letter delta is representing this partial charge. So we say that the covalent bonds between hydrogens and the oxygen are polar covalent bonds. And because of that, the distribution of charge is not equal throughout the molecule. Therefore, the molecule is polar, whereas one side of it is a little bit more negative than the other side of it. So water is a polar molecule. This is really important in nature, and since our bodies are more than 50% water, it's also really important in our own bodies and the bodies of all living things. And it is because of how this polar water molecule interacts with other water molecules and with other polar molecules in general. This figure is showing the interaction between separate water molecules. Notice that when you have multiple water molecules like you would in our blood or in a cup or in the ocean, each molecule is faced in such a way where the negative end of one water molecule is turned toward the oppositely charged end of a different neighboring water molecules. And that's because there's like a little bit of a magnet between the separate water molecules. And that attraction, although it's very weak and doesn't last for long, is very significant. This attraction is called a hydrogen bond. Hydrogen bonds are weak intermolecular interactions where two polar molecules are interacting in a way where oppositely charged sides of those polar molecules are attracted to one another. And it's called a hydrogen bond because usually a hydrogen is involved in creating the polar covalent bond. So this may be confusing to you because we have so far been talking about bonds within a molecule. So bonds that hold atoms in stable groups. And those were covalent bonds, including covalent polar, covalent nonpolar, and ionic bonds. But this bond, hydrogen bond, is an attraction between separate molecules, not between atoms of a single molecule. Because the word bond is much broader than what we usually think of it in general language, and the bond is just an attraction, and it can be really strong to hold things really tightly together and almost permanently, and it can be extremely weak where it lasts only 1/1000th of a second. Hydrogen bonds don't only form between water molecules, but between any two polar molecules where ends with opposite partial charge will attract to one another. And in this example, it's the positive end, see delta plus, is the positive end of a water molecule is attracted to the partially negative end of an ammonia molecule. And there's another example, a vague or long organic molecule that has a polar end to it is attracted to a water molecule. The shape of a molecule is extremely important to its function. It's a crucial piece of the identity of that molecule. Molecules with similar shapes can have similar functions. Let me show you an example. This is a cross section of a cell membrane. So if a cell is something like a water balloon filled with goo, liquidy goo, then we're looking really closely at the cross section of the actual latex, with the yellow here being the inside of the cell or the balloon, and the light blue representing outside part of the cell or the outside of the balloon. And on the surface, like through the latex of the balloon, there are these proteins that are called receptors. When a molecule that's floating outside of the cell, often, bumps into that receptor, it fits like a key in a lock. And when that happens, the receptor can feel the tight fit and it sends a message to your brain cell to do a certain thing. Well, a molecule of morphine happens to have very similarly shaped end part. So when it's floating around and bumps into that protein receptor, the purple thing that's on the surface of your brain cell, it also fits good enough like a key into a lock. And your brain cell thinks, oh, that's the message that Efren is sending. And therefore it has a very similar effect. This is also how any drugs that people take recreationally, it's even how coffee works too. Switching gears just a little bit, but not too much, we will connect it all together in a minute. Water is an extremely important component of life. In fact, when scientists are looking for life on other planets, first things first, they look for water. As far as we know, life is not possible without water. And water is so present in our lives that we define it kind of as a normal liquid because it's the most common liquid any of us have experienced or seen. But in fact, it's a very unusual liquid with very unusual properties. And if you compare it to other common liquids, it has some strange behaviors. Those strange behaviors are responsible for why water is crucial to life. So let's look at some of these properties of water. As a reminder, water, the molecule H2O, is a polar molecule because electrons are stuck closer to one side of the molecule, leaving the other side of the molecule less negative, therefore more positive. So if you're thinking of the water molecule as a sphere, one pole of that sphere will be slightly more positive than the opposite pole of that molecule. There are 4 important properties of water that we will discuss in several different bullet points. And they are, I'm going to look down here to read them: cohesive behavior, ability to moderate temperature, expansion upon freezing, and versatility as solvent. So let's take them one by one because they have like sub topics to each. Cohesion is the ability of water to stick to itself. That means one water molecule has an attraction to other water molecules around it. And in its liquid state, one water molecule can hydrogen bond, remember hydrogen bond, that brief attraction, to 4 other water molecules. And if we're taking trillions of water molecules in a drop, all of those water molecules are hydrogen bonded with their neighbors. And the partners are constantly switching because in a liquid, water molecules are bouncing around. But as they bounce, they switch from being attracted to these 4 partners to now being attracted to these other 4 partners and continuously moving. So if you were able to take a photo of the individual water molecules in a drop, you would see that each water molecule is hydrogen bonded with 4 other water molecules on every side. And that would be true for all of them. And then they continue to bounce around. And if you were able to take another photo 1 second later, they would be surrounded by different water molecules, but it would look exactly the same to you because we can't distinguish water molecules one from another, and we also can't photograph them. But it's a thought experiment that I hope demonstrates the point. In fact, why water drops in a drop. And have you ever looked out of the window or like on a shower door and seen a water molecule going down, 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 but then it kind of takes a side path and connects with another water droplet? Because there's an actual attraction between bits of water, whether they're drops or molecules. And it is because water molecules are polar. That is the reason for cohesion. Water molecules have polar covalent bonds, which cause them to be polar molecules and have uneven distribution of charge, which then causes them to be attracted to the opposite end of a neighboring water molecule. And this attraction between all the water molecules in a droplet or an ocean is called cohesion. The reason why many insects are able to walk on water, and if you take a picture of it, it's really cool. It looks like a piece of plastic film is over the top of the water that just gently bends with the step of the insect. The reason for that is because each of the water molecules at the surface is strongly connected to the water molecules below it and is not connected to the air molecules above. So it's like a net of connections that form the top layer of water. The force of that cohesion is greater than the force of gravity from when an insect steps on top. A related property of water to cohesion is called adhesion. Adhesion is the ability of water to be attracted to other polar molecules that are not water. Okay? So cohesion is attraction between water molecules because they're polar. Adhesion is the attraction of water to other polar molecules that are not water. You can see this demonstrated when you put glass straws of various diameters. Works best with really small straws. You put them in water, like here in a beaker, and if you just do nothing to it, you will see that the water actually rises up above the water level in the beaker. And that's because those water molecules can grab on to, it's like they climb on the molecules of glass, which are polar. This is really important for plants. Water molecules can travel through the little straws that are inside of a plant and go from the deepest roots of a tree, travel against gravity to dozens of meters up to the highest tops of a very tall tree. And there's nothing like no little tiny locomotive moving those water molecules up. It just happens because this water molecule is magnetically attracted to the polar molecule of that straw in the tree. And then when it's up here, it can feel the pull from the next polar molecule that makes up the straw, and so on and so forth. And then one water molecule helps to pull up the one that's coming below it. It's really cool system, and without it, plant life would be impossible. At least plants that are multi-celled. Water is able to regulate temperature really well. In order to talk about this, I must mention a few really important terms. So first, kinetic energy is the energy of motion. As I mentioned, liquid water is able to, liquid water moves around quite a bit when it changes these partners, right? And in that is quite a bit of energy of motion. Thermal energy is a specific measure of kinetic energy that is associated to molecular motion, right? Kinetic energy doesn't have to be just molecules moving, can be a train moving. But thermal energy is calculated based on the motion of molecules. And temperature represents the average kinetic energy of molecules. So the faster something's moving, the more kinetic energy it has, and the higher the temperature. I think you can actually see this with the naked eye if you put on a small pot of water to boil, and if you're able to watch it for a while, when it is getting hotter and hotter and hotter, you will actually see this kind of movement in the surface of the water. And that is because energy from the fire that you've lit underneath your pot is being transferred through the metal and into the water. And so it's increasing the motion with which the water molecules are moving. And if you watch it long enough, of course, it's going to start moving really fast when it's boiling. When thermal energy is transferred from one source to another, that's called heat. So heat is the movement of energy from an object that has higher temperature to an object that has a lower temperature. So when you put ice in water to cool it down, what's actually happening is that thermal energy is moving from the liquid water to ice to melt it. And because the water is losing some of its kinetic energy, it's being used up to melt the ice, it's becoming cooler. Water has a high specific heat, and that means that a large amount of energy is necessary to change the temperature of water. And this is, again, just like the other properties of water, all due to those hydrogen bonds between the molecules, because it's like a stickiness that's holding the molecules toward each other. Remember that to raise the temperature of something, you have to make those molecules move faster, which means you have to work against that attraction that the molecules have to one another. So energy has to be put in to break those bonds, and when the hydrogen bonds form, they release energy. So when you're living close to the ocean, like Santa Barbara or Los Angeles, San Diego, or Astoria in Oregon, the temperature of the air outside is continually buffered by the massive amount of water from the ocean. Because in the daytime, when there might be a lot of energy shining from the sun, you don't feel hot because a lot of that energy is being absorbed to break the hydrogen bonds in the water. And then at night, when sun is not shining anymore, the hydrogen bonds reestablish in the water and therefore release heat as energy. So it gives off heat at night when it's cold, and it takes in heat, which means it cools things down during a warm day. Compare it to locations just inland here, and you see that on a summer day, it is in the low 70s in the coastal towns, and it is in the high 90s or 100 away from the coast in California. So pretty significant difference. Another important property of water that has to do with heat is heat of vaporization. Heat of vaporization means that to evaporate water from a surface, it takes energy, and therefore it cools down that surface. So let me show you what that means. Vaporization or evaporation is the transformation from liquid state of a substance to the gas state of a substance. Water, it goes from liquid water to vapor. Heat of vaporization is how much energy a molecule of a substance has to absorb, so it has to take in from the outside, in order to convert 1 gram of that substance from liquid or to gas. Evaporation or vaporization is the transformation from a liquid substance to that same substance being in a gas form. Heat of vaporization is the amount of energy that is necessary to transform 1 gram of the substance from liquid to gas. And as liquid evaporates, it cools down the remaining surface, and that's called evaporative cooling. I'm sure you felt this when you've gotten out of a pool, that even on a warm day with a little bit of wind, you feel cold. And of course, sweat works this way to cool us down. Let me demonstrate this process with an example or an analogy. Imagine a cross-country team of runners. So it's 7 runners, and for their races, they run 5 kilometers, 5K. On this team, there are members who run 19-minute 5Ks. There's some that run 18, 10 5Ks. And then you have that one, Sally Johnson, real person on my cross-country team, who runs a 1750, can't remember exactly what she ran, a 5K, but pretty fast. If you average the speed of the whole team, you get some number, let's say 18:30 for the cross-country team. Well, if you are to take Sally Johnson out of the team, and she's by far the fastest runner, then you take the average speed of the remainder of the team, the other 6 members, and your average will be significantly lower. This is how it works with evaporative cooling. So there are lots of water molecules that are part of a wet surface. And if the fastest ones, the ones that have the most energy with them, end up moving around so much that they bounce away and are no longer held by those hydrogen bonds and they just float away, they take with them that energy with which they were bouncing. And when evaporation happens, it's always the fastest water molecules that separate and remove themselves from the group first. And when they do that, the total average energy of the remainder of the water molecules is lower. So that happens with our body as we sweat. The third really important and quirky property of water is that when this substance, water, becomes solid, when it freezes, it becomes less dense than it was as a liquid. This is really unusual. Most of the time, when things freeze, they become smaller. Even if you think about like a frozen dinner, when it's still frozen, it's like shriveled and small looking. But when you thaw it out and heat it up, it looks bigger, like it's gained size. But not so with water. When liquid water freezes, it actually expands in size. And the reason for that is the hydrogen bonds that were constantly being changed from one partner to the next now become established in a certain kind of shape. And when that shape happens, as demonstrated here on the figure, there's a lot of empty space between the water molecules. And this causes ice to be less dense than water, and therefore ice floats on top of water. We're all used to this, it's like duh, but this is a super uncommon phenomenon for solids in comparison to liquids. But it's life-altering. If the water in a lake would freeze and go to the bottom because it was more dense, like other substances, it would, for one, squash a bunch of stuff at the bottom. But two, when spring would come and sun starts shining on the surface of that lake, it would have to heat up all the water above it until the heat at the bottom is high enough to melt the ice. And of course, by the time you get heat through all the water, it's no longer warm weather and stuff is cold again. And again, the top would freeze and sink to the bottom, and eventually you would have a solid block of frozen lake where only the top surface would thaw out every spring and summer. There are many other important reasons why life on Earth would be very different if ice did not float, but those are just some examples. One more diagram to demonstrate how ice is formed when hydrogen bonds become really stable. And those water molecules are still vibrating, they're still moving, because all molecules and atoms are always moving at least a little bit, but they're not moving enough to jump out of those hydrogen bonds. Whereas in a liquid, they're constantly switching partners and exchanging their positions, and the hydrogen bonds are breaking and reforming and breaking and reforming constantly, allowing the molecules to get closer to one another and therefore become more dense. The last very important characteristic of water is that it is a good solvent. Solvent is a substance that can dissolve in it other substances. If something can dissolve in water, so you put it in, you mix it, and now it's like evenly spread, right? Like sugar in a tea, evenly spread. Then if that's possible, then that substance is called hydrophilic. Philia is the love of, hydro is water, so the love of water. If you put something in water, it doesn't spread out evenly, then that substance is hydrophilic. Then that substance is hydrophobic. Phobia is the fear of something. Hydrophobic is afraid of water. Can you think of a substance that would be hydrophobic? So I don't know what you just said, but if you said like oil or butter, then you're right. If you put some oil into water, it will just float on top in the blob, right? So oil is hydrophobic. And of course, there's a spectrum between something being very easily dissolvable in water and something that totally does not dissolve. There's everything in between. So it's not binary, hydrophilic and hydrophobic, but a spectrum. Water dissolves in it all polar substances and all ions. And the reason for that is because water itself is polar. So let's look how water can create a hydration shell around the substance that is inside of it. Here as an example is again a little block of salt, table salt, sodium chloride. And you've seen how sodium chloride is held together. So that little grain of salt that you might be putting into your soup is actually a stack of alternating chloride ions, so negative ions, and sodium cations, positively charged sodium ions that are attracted to one another because they're oppositely charged. When you put this grain of salt in water, the water molecules, which are constantly moving around, they eventually bounce into this block of table salt, and the positive ends of different water molecules make a sphere around each negatively charged chloride anion. And the negatively charged ends of water molecules create a sphere around the positively charged cation sodium. So they kind of all bounce together with these hydration shells. So when one ion is separated from the other and completely surrounded by water molecules in a hydration shell, that's what being dissolved means, is that the molecules of the liquid, in our case water, are completely surrounding the substance that's in the water, and they don't let it to clump with other pieces of that substance. This purple blob is representing a large organic molecule in our body, so probably a large protein, and it can exist in a watery interior of a cell because it has these polar parts to it that water can become attracted to and therefore surround. So within each water molecule, oxygen is really electronegative, meaning it pulls electrons really strongly, and hydrogen is not able to compete with that. So oxygen pulls electrons toward itself away from the hydrogen, and once in a while, but very consistently, the oxygen rips one of the electrons from one of its hydrogens completely. And therefore, that hydrogen is like, oh, and it floats away like what's her face in the space movie, right? So they separate. And in this way, a water molecule can break into two parts and create two ions. Two OH minus, which is called a hydroxide ion, and H plus, which is a hydrogen ion. The hydrogen, to begin with, only had one proton in its nucleus and one electron outside of it, which it was sharing with water. But that oxygen ripped it away, and now that hydrogen actually is just a proton. So in this case, it's literally just a single proton, which we here write as H plus because it's a hydrogen cation, just floating around. And the other half of what used to be water now has actually gained an extra electron. And so it is also an ion, but negatively charged, and it has an extra electron. And it seems like a random fluke thing, but in fact, if you take any amount of about the same proportion of water molecules be split up at any given moment, 10 to the negative 7th moles per liter. And if that doesn't mean anything to you, which it probably doesn't unless you've taken some chemistry, then don't worry about it. It's just a certain small fraction of all water molecules will be broken apart at any given moment. A lot of times it just happens for a second, and then the ions will combine back together to form a normal water molecule. But at that same moment, somewhere in the vicinity, another water molecule splits into two ions. So the percentage of water molecules that split is really small, but is constantly happening. And the reason why this is important is that this is what determines a pH of a liquid that is water-based. So in water that's considered neutral. Sorry about the sound there, my microphone fell. pH, we don't actually know exactly what the P stands for because the scientist who was first describing it used it for several different things. So either potential of hydrogen or power of hydrogen. But either way, pH is an measurement of how many of these free floating H pluses, so hydrogen atoms that have lost their electrons, are floating around. And the reason why it's important to know how many of those guys are floating around in any kind of a liquid is because they are very reactive. They're super unstable on their own, so they'll be like jumping at things and attaching and bouncing into stuff, which change the chemistry of wherever you're at, or it can actually disturb and break things inside of a cell or in a living system. To measure the pH, we have to take the negative log of the concentration of hydrogen. So pH is determined on a scale from 0 to 14. So if you add something to a liquid, and because of the structure of that thing you're adding, you, for whatever reason, increase the amount of free-floating H pluses in that liquid, then that substance you added is considered to be an acid. If you add something to a liquid and that substance directly or indirectly causes there to be less H pluses, then that substance is called a base. So let's look here. I really like drawing this on the board to show the process, but I can't do that right now very well. So go ahead and draw it in your own notebook. A neutral solution has a lot of H2Os, classic water molecules, and a few that have been separated. So notice how there is an equal number of protons or H pluses and OH minuses, equal amount. Then on this side in the solution, there are some more H pluses than there are H minuses. So that solution is now acidic. And if you were to add it to neutral water, that water would become more acidic. Whereas on the opposite end, you have a water that has more OH minus dissolved in it, which makes it a base. Another word for a solution that is basic is to say alkaline solution. So the pH scale goes from 0 to 14. And how it's measured is you take the concentration of free-floating protons or H pluses, hydrogen ions. It's 3 words for the same thing. H plus, hydrogen ion, and protons are all talking about the exact same thing. So if you take on your calculator negative logarithm of the concentration of how many of these free-floating hydrogens you have, of course you can't calculate them yourself, I would have to provide that information. But if you do that calculation, it'll give you a number between 0 and 14. If the number is lower than 7, then your substance is acidic. If it's higher than 7, it is basic or alkaline. And if it's 7, it's neutral. So here's the trick. Because the math to calculate this is the negative log of something, that means that the more free-floating protons or H pluses there are in a solution, the more acidic something is, and the lower pH number. So stomach acid has a lot of protons dissolved in that liquid in your stomach, and therefore the pH of your stomach acid is 2. So a lot of free-floating protons equals to a low number on the pH scale. Whereas something like a car battery is extremely basic or alkaline, but so it's a high number, but it has a small, relatively speaking, amount of free-floating protons. We often talk about strong acids being really dangerous.